Ago. I gave a talk last year that was about geospatial data projection, and it was kind of a high-level talk, but I felt like I didn't give people good enough tools to actually do what I was talking about afterwards. And by data projection, I mean basically if you draw a shape on the United States, if you have the right kind of data, you can tell how many people like cats in that shape, you can tell how many people like cruises, how many people like cats and cruises in that shape. Even if it's a completely novel shape or several shapes that no one's ever seen in the history of humankind, you can project that data. So I went to a talk last year by Catherine Devlin about IPython Notebook, and it seemed to be the right solution to make sure that I can hand off the right tools for everyone to do this. So we're not going to talk about data projection so much. We're going to talk about the building blocks for using Shapely and using any kind of 2D spatial data to do almost anything. And on top of that, I'm going to give you as much code as I can. I'm going to give you denoisers. I'm going to give you things that read stuff out of, read shapes out of files. There's lots of free data out there. I'm going to give you whatever I can. I'm not going to talk about it so much. It's just going to be here for you to use and copy and do whatever you want with. So that's the idea. So anyway, welcome to the care and feeding of 2D data using Shapely. I'm Alison Alvarez. I work for Risa Labs in Pittsburgh. And a lot of my job, at least up until recently, has been building and refining our geospatial data sets. We have a lot of clients who have unique sales territories, and they want to know exactly what's going on those sales territories at all times. And so it's my job to take spatial data from anywhere and basically glue it together to make these territories, and also make those things so they're pleasing to look at and don't look like a pile of trash, which we'll talk about how to detrashify your shape data as we go along. So of course, I've learned a lot from other people. Here's some examples of other Shapely IPython notebooks with the links. And if you want the GitHub or the NB viewer of this, I've got links also, and as well as a link to the Shapely manual itself. There's a ton of stuff in there. We're not even going to hit 25% of it today, so it's there in case you need it for whatever your needs are. So first, let's talk about the kinds of things you can do with the Shapely package. So, for example, this is Conway's an example of an implementation of Conway's Game of Life, only without the usual grid. You can basically draw, so you don't need discrete points to draw the life forms. You can draw them anywhere. And if you're familiar with the rules of the game, if you're by yourself, you die. If you are overcrowded, that means you touch more than 3 other life forms, you die. If you only touch 1 life form, you die. But if you touch 2 to 3 other life forms, great, you live. You can implement that using Shapely. Another example of something you can do with Shapely, and this is more in line with the kind of thing that I do, this is the state of Georgia. And this is actually 3 different kinds of alcohol consumption data layered over each other. So you see that sort of God's people live down here in Georgia on the coastal plain. Can you guess what these dark patches are down here in below what we call the fall line? Do you have any guesses of what's located there? What? Exactly, military bases. A lot of people guess college towns, but yep, nope, that's Moody, Warner Robins. Yep, that's where the alcohol is, folks. Okay, and here's another example. We had a data contest internally at our company to show just different applications of what you could do with Shapely. This is from our CTO. He basically drew his cat Luna out in the ocean using Latin long points, and then building sort of radii around those circles, around those Latin long points. And he drew Luna out into the ocean just to show how it's possible to use different color values and different sorts of grids to build sort of these dynamic data sets whenever or wherever you want. And so here's the original photo that he used. He gave it to me this morning to make sure it made it into the presentation. So proper credit to Mike Higgins. Okay, so before we get started, here are the packages that we're going to use to draw this stuff. If you look at the README in my GitHub, I linked to most of these packages so you can figure out how to install them. It's slightly different between OS X and more Unix-based systems. So I did my best guess at how it would work, and otherwise I linked to the documentation so you can figure it out yourself. And so here's our first block of code. We're not going to spend a lot of time looking at this. This is how we will actually draw the shapes with the help of matplotlib. I borrowed some of that code itself, and there's credit to the IPython notebook I borrowed it from. I added a few things, mainly extra control over color, because color is really good for indicating whether things are separate or not in Shapely. So let's start with our first thing with Shapely. Oh, it's amazing. It is a point. So it's right here in the middle. All right, that's not super interesting, but we can use something called buffer. Buffer will basically, if I give it a value of 1, it'll basically draw a circle with a radius of 1 around that center point. Buffer is the duct tape of the Shapely library. So it is one of the most useful things there is, and you'll see it a lot in this presentation. So okay, we got a circle. Fantastic. So this is what that circle looks like in text. You can see its individual points outlined there. This is called WKT, well-known text. There's also a WKB library that comes with Shapely. You can also draw multiple shapes on top of each other, as well as use the difference function to subtract one shape from another. So this is sort of negative space here that I'm indicating. So now we have just one shape, and instead of having two shapes with exterior rings, we've got one with an exterior ring, and now we have this interior ring from where we subtracted that shape. So let's also look at one of our other primitive forms. We've got a line thing that goes between 2 points, all right? Line's pretty easy to understand. There's also line strings that are just multiple lines put together. And when you combine them with polygons, you can have a sad bunny. So here's a sad bunny. That's, aw, okay. So here's another more complicated polygon with holes. So for example, you can see this is basically a square with two holes that touch by 1 point. Touching by 1 point, okay in Shapely. Touching by more than 1 point, bad. So you can see that this first tuple right here lists the points in that exterior shape, and then it's followed by two tuples, which are the interior shapes. So you can see them all together at once. And then if we traverse those rings, you can see just the printout of like what's what. So basically, you can use some of the primitives in Shapely to just sort of print this whole thing out, and we'll use that quite a bit just because some of the operations treat holes different than lines, and we might not necessarily want that. Okay, so let's talk about combining multiple shapes. So we've got a circle and our square that we just looked at here. So what happens when we combine them? So we get this new circle square thingy, and that's just dot union. Very simple, one thing dot union another thing. And what happens, so what we do is we get a brand new polygon. So what happens when we put together two things that are disjoint? They don't actually cover the same space. We get what's called a multi-polygon, which is basically multiple polygons put together. And each of those polygons carries their own set of holes with them. So they basically keep it as their own package. And that's actually important when we talk about Esri in a few minutes. Are you guys, any of you guys familiar with Esri, the mapping situation? Okay. We're going to talk a little bit about those file formats and why this stuff looks different. So anyway, fun times. You can see all the pieces of our new shape. And you can also see the new area. So you can see that we went from having 12 plus 14, that's 26. So we basically combine our two pieces into our new big thing. And so when you calculate the area, it takes into account all the pieces. Okay. So let's talk about how we get shapes from a file. So this is where Shapely gets to be really, really handy. And there's a companion package called Fiona. And this is the basic code for just importing a file, a shape file specifically, using Fiona, and then just looping through the pieces and then saving them basically as a dictionary with a key, and then the value being the shape. And once you have that, you can do tons and tons of different things. And also, I've included a link here to the US Census, USGS archive. Tiger provides this. All of this stuff is free. Your tax dollars provide it. So when you're paying taxes and you want to get something back for it, this is one of the most valuable things that our government gives us, is these shape pieces. They've got counties, zip codes. They're actually called ZICTAs. We can talk about the history of zip codes later on. I know it's a hot topic, guys. So we could talk about that. There's shapes. There's all kinds of tracks, census block groups, and you can do so many things with these. They are free. They are unlicensed. You can do whatever you want. You can make money off of them, which is one thing that my company does, and they're just there as an asset for you as a community. And using the Shapely package, you can turn that resource into a real thing that you can build maybe a business off of. So moving on. Here's what, when you crack open one of those shape files, here's sort of the ordered dict that you're going to get out of it. And so you can see there's a lot of information here. But the thing we care about really is what is the name of the shape. And in this case, we've got Illinois and Florida here. There's also some information about the amount of area that's covered by water and land. And we'll talk about that in a little bit too. So anyway, let's pull out one of our shapes. We've got Ohio. Okay, we're in Ohio right now. That's appropriate. So here's Ohio. Ohio looks a little weird, doesn't it?
That's a tiger shape?
Yep, that's right. So Ohio looks a little weird. So here's one thing that the USGS does, and they don't do it always consistently, so I'm just going to warn everybody about this. There's actually a big chunk of Lake Erie included with this shape. So you see this line right here from there on. There's actually like this banana shape. And if you look at Pennsylvania, you know how Pennsylvania kind of has that cowlick on the end of it? It also goes up into Lake Erie. And if we look at a bunch of state shapes all at once, you'll see that Michigan is basically kind of a big mess. But this is just so that the water territory for those states is included with the shapes. And that happens sometimes, but not all the time. And how do you get rid of that? You can use another shapefile from the USGS that's better at cleaning this stuff up. So you can take all the county shapes together, union them together so that you have your new state shape, and then you can subtract that from your state shape.
Does Shapely deal with the projections?
No. Well, you might have to write something on top of it. So we treat everything like it's a Mercator projection. So everything up north ends up being kind of big. Things down south towards the equator end up being kind of small. I'm going to show you an equation at the end of this presentation on how you deal with that using the Great Circle equations. And if you don't remember trigonometry, you might like using the code that I have here so that you don't have to worry about doing this yourself. So anyway, moving on, here's what Michigan is supposed to look like. You can see all the individual islands. So quick digression, does anybody know why Ohio and Michigan hate each other so much? It's also the same reason why Michigan's southern border is uneven. Do you guys know why? Toledo War. It's all Toledo's fault.
Yes.
Yep, it happened in 1835. It was a battle between the two states. There were territories at the time for the Toledo Strip. Only one person was hurt. He was stabbed by a penknife over Toledo. So.
And we lost. We got Toledo.
Yep. But Michigan also got the UP out of that, which is why it's not part of Wisconsin, and that's why that weird non-contiguous state exists. Anyway, moving on. So let's talk about simplifying shapes. So this is one of the coolest things that Shapely can do. So as you can imagine, with anything that's 2D, there is a huge risk of basically it's really expensive time-wise to run some of these queries. Or to do some of these operations. And it's because you're dealing with 2D space, which means n-square algorithms are a real hazard of doing a lot of these things. So simplification can sort of take the edge off of some of that hazard because you can take a shape with lots of nooks and crannies and basically make it a lot simpler, because to the naked human eye, in a lot of cases, you don't need to see 50,000 points, but 4,000 might be just right depending on what you're doing. And if you're doing really crude calculations, you might even want to take it lower than that so that you don't wait a million years for these calculations to finish. And I deal with all the zip plus 2 shapes in the United States. There are 600,000 of those. It is no joke to deal with those things at full strength. Okay, so let's see how this simplification works. Here is a little bit of code that'll show you how to count up the points in a shape, because you do need to count up the interior and exterior coordinates separately. So let's take a quick look at Hawaii. And so one of the first things we're going to look at is basically how this gets simplified in 2 different ways. So Shapely has a flag that's called preserved topology. And preserving topology means I try and do my best to preserve the shapes that are here. So I try and not throw out shapes. And I try and try and keep as much of the footprint as I can. But you'll notice here that when you try and preserve the topology, it actually takes an order of magnitude longer to do that. So if you're trying to do something in a timely manner, say for example in real time, preserving topology might not be a great idea. However, if you look at something like Hawaii, which actually is a lot longer than I thought it was going to be, there's a lot of islands in that archipelago. So this is preserving the topology. So you can see it kind of got like a little, this stuff got a little bit crude, but if you don't preserve the topology, you'll end up losing a bunch of the islands, which people in Hawaii might not want. So let's move on and take a little look at the algorithm that's used to do this. It's called the Douglas-Poiker algorithm. On the Wikipedia article, it's the Raymer-Douglas-Poiker algorithm. And this is just a little GIF to show you how this works. And this is the one that's used for that quick topology simplification. So this is just sort of a quick view of how that works. So, you guys familiar with Texas? You guys know what Texas looks like? Lots of panhandles. But it's a pretty complicated shape. There's a lot of coastline, riverline. So what you can do is, you can start with the shape. It's 50,000 points, 58,000 points. That can be a lot to deal with. It can be a lot to store in a database. If you want to union it with something else, that can also be really complicated. So what you can do is sort of just take the edge off. So you can simplify, and this is just sort of this 0, 0, 1. It's just sort of a threshold factor. It's not from 0 to 1. It's actually, you can go above 1, far above 1 if you want to. And so this looks the same to the naked eye, so that might be a win. The only problem is if you're trying to join a bunch of shapes together, what happens, and this will probably be better illustrated by this shape, if you take it one step further, is that it kind of gets kind of crude and you have all these curved lines that sort of become straight lines. And if you're trying to union shapes together, you end up having overlaps and then you have gaps. And that can end up making things look a little bit messy. We'll talk about how to fix that in just a little bit, but that's just something to keep in mind if you're going to simplify stuff. However, if you're just going to screen print this or do something pretty simple with it, this might be exactly what you need, and it's only 47 points. That is a bargain, guys. And if you go take it real far, so here's a 1.1 level of simplification, then you get a Flintstones version of Texas. So that's not really useful to anybody unless you're trying to do something really, really simple. So there's a couple of other operations you can do to sort of deal with your shape. We actually use Convex Hull quite a bit. And this is basically throwing a shroud over Texas. It's basically a convex shape that the smallest convex shape possible that will contain all the points of Texas. And this is pretty quick to calculate, and it's really useful for if you want to show people sort of a border area without all the dots and lines that might show up in your original geometry. So this just makes it a little simpler to just show the complete coverage of your shape. Another easy thing to do is, this one's super cheap. Oh yeah, guys. Envelope. And so the companion to envelope is bounds. And bounds just basically gives you the 4 corners that will contain your shape. I use bounds for quite a lot of things, just for checking candidates to see if some things will line up against something else. So these are just sort of handy general functions that you can use to run tests on your shape and basically compare shapes to other shapes in a cheap way, because remember, 58,000 points, that is not a joke. So you can also do the centroid of a shape. So this is not a weighted centroid. So if this was a weighted centroid, the center of Texas would probably be pulled out over here. Basically, it's a very simple, very cheap calculation. It's the bounding box, and then just each of those measures halved. So you can see I just sort of drew a little bullseye right here on the center of Texas using my friend Buffer to sort of just illustrate this point. And we use centroid for quite a bit, just for sometimes overlaps are a little too generative, like if things just sort of kiss up against each other. Shapely will say, yes, those things overlap, and sometimes you don't want to know that. And so we do contain center sometimes, just because it ends up offering us a cleaner set of what overlaps with what. Okay, so moving on, let's look at a couple more Polygon operations. So there's 2 operations called Cascaded Union and Unary Union, and what you can do is just draw a bunch of buffered points, and you can basically pass the cascading union just the list of those, and it will fuse them all at once. And this is a little bit cheaper than doing the loop-wise union. So I'm going to warn you about this one because I hit this last weekend. So it is possible to get into an infinite loop, or what seems like an infinite loop because it will run for 2 days without doing anything. If you're using really, really complicated shapes and you're trying to union them together. Cascade union will just go away and not come back. Shapely is based on top of a C layer, so sometimes it's really hard to see what's going down in the harder Shapely. And when that happens, you can wait 2 days and then be like, where's my answer? And you don't know if it will take the heat death of the universe for it to actually come back with something. So I recommend, if you're dealing with something more complicated, to use any kind of time test to sort of like time out things that take too long, or use that stepwise union, because that will at least fail faster and not let you down in the way that cascading unions will. And there's also Unary Unions, which are a little bit more robust. It's just so you can fuse lines and points together with shapes. I don't know why you would do that, so but it's an option if you can think of a good reason to do it. Another thing you can do, so I'm just going to take these first 2 points out of this list, and we're going to just look at those 2 guys closer. So another option you have is intersection. That should not be surprising, considering that I've been talking about unions. And what's really nice about intersections is that it's a symmetrical operation. So you can A intersection B or B intersection A, and you're going to pretty much get the same answer, which is this weird brown thing in the middle. And so you don't have to worry about covering both sides of that operation. The opposite option is difference. So basically, what are the differences between these two figures? So it's whatever's not in the other guy. And this is not a symmetric operation. So A difference B and B difference A, they'll give me 2 different answers. However, there's symmetric difference if you want to go ahead and have that work out in both ways in your favor. So that'll just take out, it's basically your 2 shapes union together, but with that intersection subtracted out of the equation. Okay, so now we're going to talk about broken shapes. So it's actually, so you basically end up having a contract with Shapely. And the idea is that you're going to give Shapely valid shapes, and it will give you back something, hopefully, that means something. And if you don't give Shapely a valid shape, who knows what could happen. And we're going to see some of the examples of things that you may not be expecting that could happen to your shape if you're not careful. So let's just talk about a specific example. So there's a function called explain validity, and it will just tell you if your shape's okay, it'll say, valid, and otherwise it'll say exactly what's wrong with it. And based on what's wrong with your shape, you're going to want to do different things. So for example, in this first guy, I've just got a line sticking out of a shape, and Shapely hates this, and it's not a valid shape anyway. So you can use your friend and my friend, Buffer, who will basically draw a thin little veneer around your whole shape. This is even exaggerated a little bit so we can actually see it, but it'll just draw a thin little shape around it. And now your line has gone to actually being a very, very skinny rectangle. And now you are back to having a valid polygon, and you can do whatever you want with it. Victory. Okay, so let's see another example of self-intersection. All right, so here's the bow tie. And you know this one's especially bad because it says the bow tie's area is 0. And that does not look like 0. But again, Shapely, you have a contract with Shapely, and you broke it by giving Shapely a self-crossing shape. So this bow tie it can be the death. So let's see what happens when we use our friend Buffer and we draw that around our shape. Oh no, we dropped one of the polygons. So this is kind of scary if you're working with large chunks of data, and you're letting it run overnight, and just poof, pieces of your shape can just disappear into thin air. So I recommend not making this shape if possible, first of all. So just so you know. And second of all, what I do is I have tests that tell me as soon as possible if I have one of these this unexpected kind of shape disappearance, I basically have something that emails me so that I can see it on my phone, and it says, this thing broke in this very specific way, so I can take evasive action immediately. And because sometimes, like, Staten Island will just disappear into thin air, because Staten Island is weird somehow. So generally what I do to take care of this is, any of you guys familiar with the concept of annealing? So you guys know local minima and maxima. Basically, you can think of like getting stuck at local minimum and maximum as like you've got your graph in a box, and there's a ball in there, and you shake it, and then sometimes it goes down to the minimum, sometimes it ends up somewhere else that's not the minimum. I basically do the same thing when it comes to these kinds of shapes that screw things up. So I've got something constantly checking to see if things are valid, and if things are invalid, and a piece of it disappears, like all of a sudden it goes from having a certain area to a very, very small area, then that's a problem. And basically what I do is I shake the box, either using a different degree of simplification or by going back to my component pieces and hunting down the one that causes the problem if possible. And I try and do this in an automated way because I want to go to bed. And this stuff takes a really long time to run, and so you have to make it as automated as possible when you're dealing with national level geographies, especially when you're dealing with lots and lots of really tiny ones. Okay, moving on. So I also thought like I would be really slick, and I just patched the middle, like a little Band-Aid in the middle. So Shapely actually pukes on your feet if you do this. So here's the stack trace, and I basically copied and pasted the stack trace in here because, as you know, IPython Notebook hates it when things actually throw up. Like everything downstream gets a little pretty sad. So here it basically says like I have a null geometry. Poof, nothing happened. I have nothing here. And you're like, I gave you this awesome bow tie, and it says that bow tie stinks. And so at least Shapely is honest. Yeah. All right. So let's talk about all the things that can go wrong with holes. So the first example, you can basically draw a hole that's outside of the shape, and that is wrong. You can see that is wrong because I have these two holes in my shape. So the shape I drew here is 4x4 grid. 16 points in area, and then each of these shapes is just 1. So I should have 15 in area with that point outside, but no, since it is a hole, it is subtracted from everything, and I end up with my wrong area. That's a little annoying. So again, my friend buffer, and I can just send it a buffer of 0, so it really just draws a shape around my shape with no extra space, and then my shape is happy. The area comes out correct, and so that's one way of fixing it, and my favorite way. You can also just run through everything, and if you have a hole that isn't inside any shape, you can just throw that out, and I'll talk about how to do that too. Okay, now you have nested shapes. Same issue where you've got a shape within a shape, and you basically end up double counting the negative area. And again, buffer, awesome, gone. So again, duct tape. It's great for a lot of things. So here's our last example. So like I said before, when you have two things touching at a point, that's okay. When they touch by more than one point, bad. In this case, we don't get the discrepancy in area, but it makes some of the union and intersection calculations, it can kind of screw them up a little bit. So again, buffer, poof. So good stuff. So let's talk about the last one, and this one, for the longest time, was my nemesis as an unsound shape. So really, when you simplify things, sometimes things get so simplified. I'm going to show you what this line actually looks like. So you might notice that this line, it's a line. It looks like it has lots of points, but basically, sometimes when you simplify a lot, they basically get squeezed down into being 2 points, essentially. And you can't fool Shapely by putting like, 3,3 a lot of times. Shapely knows, and it's wrong. So basically, what you have to do is traverse through that shape And you can basically find either if you're a multi-polygon, you can find the extra polygon that's not the right number of points, or you can find the interior polygon, your hole that's just 2 points, and you can toss that sucker on the ground. And you know what? I have the code for you to do that. So if you find this little rotten jerk anywhere in any of your shapes, I recommend using this, because buffer won't necessarily cut it, but this will. This is basically RAID for these little guys. And when you deal with really, really complex shapes, so anything that's like an archipelago, the coast of South Carolina, North Carolina, anything that's in Hawaii, Alaska, oh boy, Alaska. These islands can make these things really, really complicated to deal with. And because, especially with Alaska, you've got a really high volume of area and these really small, tiny islands. Those little tiny islands can really just get, if you do simplify and you get rid of all the fat, sometimes you start it on the muscle, and that can sort of create these errors. And this is just one way to handle it. Yeah.
So this is all about validity of shape files coming out of the Tiger database.
Well, sometimes. So okay, generally the stuff you get from Tiger doesn't have this stuff in it. Where these sort of these errors get introduced is when you start unioning things together, and then simplifying especially. And even preserved topology swears that it won't introduce any invalid shapes. I have found that not to be true in my experience. However, there are shapes that do come from vendors and sometimes from Tiger that are invalid from the get-go. And it could just be somebody was not paying attention when they were drawing the line on the map, if they're a GIS person. It totally happens. So I believe in trust but verify. The explain validity is actually not a very expensive operation to run. So I run it on everything every time I do something to a shape, because entropy is everywhere. Okay, so my gift to you guys, fixing all these holes. Okay, so we're going to talk about, there's my fixed shape. Oh, it's a beautiful rectangle. Hooray! I guess it's a square, which is a form of rectangle. All right, so we're going to talk about one last piece here. And this is actually kind of a hard-fought piece when it came to implementing our system. So we get zip codes from outside vendors. So zip codes are actually not a 2D shape, believe it or not. Zip codes are actually identify a postal route. And it's like Social Security numbers. They were never meant to do all the things we do with them. And we do the same thing to zip codes. They're not actually a map object. So the USGS provides something called a ZICTA that sort of approximates these postal routes. But some of our clients don't like those ZICTAs, because if there aren't any people there or anybody to get mail, then generally there's no coverage. So there's a lot of swampland, let's say between Georgia and Florida. There's no zip codes there because there's literally no ground. But our clients don't like seeing that kind of empty space, because to them, that space is where money is. So we use a lot of private vendors to provide zip code data. These zips are from zipcodes.com. I do not recommend them. Because when you take their raw zip shapes and you fuse them together, you get these little artifacts. Because basically, whoever drew these zips wasn't looking at all the shapes around the zip codes when they drew them. It's like they were just tracing something and they didn't do a super great job. So you end up with these little artifacts here that look terrible. They make a shape really expensive to store in the database. The indexes end up getting really expensive if you're storing it in any kind of MySQL or any other kind of database. They stink, and they look bad. And because it's like, what is this thing I'm looking at? When it should be a very clear sales territory. So let me show you how to fix that. And I'm also going to give you this code for free. Look under your chairs, there's code. Anyway, so let's talk about a specific instance of this. So we're just going to look at Jacksonville Beach here. Very simple. Here are a couple zip codes that we're going to fuse together. Okay, no problem. Well, there's all these little artifacts in them. And this looks kind of bad. This is not as bad as what we were looking at before, but it's still kind of noisy and annoying. And so what you can use is basically the smoothing algorithm that I have. Smoothing is not the right word for it. The denoising algorithm that I'm going to show below this. And basically what you do is you look at all these little pieces that are very annoying, and you say, hey, what is your area? And if you're doing an application in, say, biomedical sciences, and you're doing this kind of denoising, good. You can just say, set a specific point threshold, keep what's above it, throw away what's below it. However, we are using the Mercator projection, which is like sometimes a projection for doofuses, because Greenland ends up the same size as Africa. But in our case, it means that our calculations can be really simple because we treat everything like it's just a giant grid. However, it means when we do these sort of denoising things, things up north end up having much higher point sizes than things down south. And so we have to sort of take that into account. So I'm going to give you guys math to fix this. And so this is great circle distance. So basically, we draw a bounding box around the offending shape. And we use the great circle distance to sort of normalize that shape according to how far north it is. And then once we do that, we can figure out what the square mileage is of those individual shapes. So those little bits of confetti that end up in your shapes, you can basically treat them on an individual basis. So even if you have the whole nation of it, you can treat stuff up north different than the stuff down south. And now that you have the true square mileage, you can actually set your threshold with just a mileage base, which makes sense, brain-wise, maybe more than points on a grid would. And then you can truly throw out things that are too small and too big in the right situation. Now, if you're using this for a not geographic situation, congratulations, you don't have to worry about great circles at all, and you can go do your own thing. But I included that just in case people wanted to figure this out, because it's actually not that intuitive. So anyway, that's the end of my talk. Oh wait, there's one more thing. I'm going to show how this algorithm works on Hawaii. So basically, I threw out all the islands that were smaller than 250 miles because I can. And that's basically what happened here. Anyway, that is for real the end of my talk. All right, thanks guys. So, question?
Yeah, so can you actually take a zip code with those routes and go back and pull in the census block groups in order to create an area?
Yes, you can.
Please repeat the question.
Sorry. So can you take a zip code, and if you know the census block groups that overlap a zip code, can you take that and rebuild the zip code out of census blocks? And to some degree, you can. So one tricky part is that census block groups do not line up cleanly with zip codes. So they can be split between different census block groups. But you have the power of Shapely, and so you can weight that if you find some sort of algorithm and basically cut the census block group in half, and divide that sucker and give it one half to one guy and one half to the other guy, and you're good. The algorithm for doing that might depend on what you know. You might have two concave points that you just link up together. It really depends, and you can actually use a distance algorithm, or you can basically just grab those 2 points, create a line, and then use that line to divide your Shapely object. Any other questions?
It's a matplotlib based, right?
Yep.
Do you know if this translates well to the sort of the matplotlib conversion, like Plotly or MPLD3 that makes it, that allows you to sort of do interactive viewing in the notebook, like zooming in, zooming out?
I haven't actually used that yet. That's very interesting.
Most of them have like these nice, hey, just convert your fig to Plotly. So I was wondering how that's translated. Sometimes they get, with polygons, they can get a little confused.
Yeah, I have PyPlot. There's actually a patch for matplotlib specifically for polygons that I import for this, so that the polygons actually get drawn correctly. And if we have a few minutes, I want to mention one thing. So if you guys pull in this raw data from the USGS, it's written in Esri format. And what happens is that all of the external coordinates are clockwise, and all of the interior coordinates are counterclockwise, and they're just sort of all grouped together. And the thing with Shapely is what they want is all the holes to be grouped with their exterior shape. And so if you write your own parser, if you decide that you don't like Fiona for one reason or another, there's a function inside of Shapely called isCounterClockwise, and you can use that to divide those shapes into the right place. Occasionally, they get flipped around in Esri. I don't know how that happens. So you might want to do some tests just to make sure things contain other things. But that's one thing you can have in your back pocket if you decide that Fiona doesn't work for you for one reason or another. Yes?
We have time, 8 minutes.
Oh, great.
So are you running this on your desktop, or are you running it on server environment?
So I have a box that is in a closet at my company. Its name is Mantis. And that's generally where I run this stuff. I actually have something going right now that's rebuilding all of the, so you guys are familiar with Comcast, right? So it's rebuilding all of the Comcast ad sales territories right now, and then we'll do our monthly release.
Now, have you linked this in with anything like GeoServer, where you're actually like doing overlays back into tile systems or anything?
We do that. So we use Mapbox. And this is actually from the stuff up here is actually from our system. Like we use, I think we're expanding the stuff to have a lot more tiles available, but this is all about drawing stuff on top of tiles so people can see what the heck is going on here. This is directly from our system. So you can basically pick out whatever shapes you want to draw them directly onto a map.
And the last question from me, does that tie back into anything with like PostGIS, the GDAL, Geo stuff? Python library standard?
So GDAL, so actually Fiona has a dependence on GDAL, so it's definitely something you need if you want to use this stuff. And I use PyLab and a few other things. I think there's SciPy and NumPy gets used in here, but it shouldn't be a surprise, I guess. Any other questions? Yes?
Have you ever tried using basemap for your projection?
Yes, and actually one of the, sorry. Oh, sorry. Have I ever tried to use, I'm terrible at this, sorry. Have I ever tried to use basemap for any of my projections? Yes, and basemap is actually a pretty good option for this stuff. You can make really beautiful notebook images with this. There's actually, if you go up to the top, some of the other notebooks that I linked, there's one that does use that package and to draw different sort of mineral territories in New Jersey. It's gorgeous. So it's definitely an option. I went with the easy thing, which was Matplotlib. Any other questions? Okay, great.
Thank you.
Thank you.